So now we'll come to the final topic in our linear algebra course, which is eigenvalues and eigenvectors. So eigenvalues and eigenvectors basically comes from the idea that if you have some vector x that belongs to Rn, okay, and there is some lambda, which is a scalar, okay, lambda is a scalar, and A is an n by n matrix, and A is an n by n matrix, then there is a very interesting relationship between these three. And that relationship is in this small, simple equation. That there are certain values of lambda such that this coefficient matrix A, which is an n by n matrix, times this magic vector x equals lambda times x. So what we're saying is this equation is basically saying that the role of A is encapsulated in this one scalar single value. And of course, with the help of this x here, which is known as the eigenvector. So this magic value is called the eigenvalue. Okay, and this magic vector is called the eigenvector. So now that we know by definition what these are, let's try to see how we could actually calculate eigenvalues and eigenvectors. Well, if we rearrange the above equation, we can rewrite it as A minus lambda I into x equals the zero vector. Now, what I've done here is, if you're confused about where did this I come from, if I bring ax to the other side, if I bring everything to one side, I get this, which should be obvious. Now, when I take the x out common towards the right, I can't leave a scalar sitting there. So I need to multiply it by the appropriate size of matrix. So here, this I that you see is an n by n matrix, okay? And it's the same size as this A, which is also an n by n matrix, okay? So I'll show you in an example what it looks like, once we get to the example. But for now, please keep in mind the I is introduced to enable the actual mathematics to occur. Because remember, addition and subtraction of matrices, the two matrices here, A and lambda I, must be of the same size. Okay, so let's move on. Then, once we've done that, once we've got this, now let's look at this system of equations. This is a homogeneous system. A homogeneous system of equations. Now, keep in mind that x equals the zero vector is the uninteresting trivial solution. So, what we want to do is, we want to look at those x's and lambdas that give us infinites that are non-zero, in other words. So that would happen when this system has an infinity of solutions. So it has infinite solutions. Okay. Now, if it is to have infinite solutions, what condition must be imposed? Well, the first thing is that the inverse of A minus lambda I, so that means that this matrix A minus lambda I must be singular. Okay, for the infinite solutions, that is a necessary condition. A minus lambda I must be singular. If it is singular, we are guaranteed there will be infinity of solutions. So let's see how we could get that to work. Well, if A minus lambda I must be singular, there is yet another condition that can help us, which, as you know, is that singular matrices have this condition, that the determinant of the matrix is zero. So that means that, remember, the only flexibility we have in this equation is the lambda. In this one, it's the lambda in the x, of course. But here now, all that's left is the lambda. In other words, the lambda can help us manipulate this matrix and try to see, and we can try to see if we can work out values of lambda that will make this determinant actually 0. Now this is in fact called the characteristic. Now what will happen is, before I go, it's called the characteristic polynomial, but before I go there, keep in mind that this is the determinant, which means this is a scalar quantity. So what you're going to end up with is going to be an equation in lambda. So what's going to happen is, if this is an n by n matrix, we're going to end up with this implies lambda n, okay, plus let's say a1 lambda n minus 1 plus a2 lambda n minus 2 a n lambda to the 0. So this is equal to 0. This is known as the characteristic polynomial. Okay. So this characteristic polynomial will have solutions, and those values of lambda, each one will give us a corresponding vector x, and that vector x along with the paired lambda will satisfy this relationship, this very interesting relationship. So in other words, the steps in the process are to for a particular matrix A, the steps are to get to this characteristic polynomial, solve the characteristic polynomial, find the values of lambda, and then find the eigenvectors. And those eigenvectors and eigenvalues are basically what we are in search of. So let's move on then to an example. Let's start easy with a 2 by 2 example. So here's a matrix A, 1. So let's look at this matrix. Now if I want to find the eigenvalues, so in other words, what I'm looking at is this situation. Ax is equal to lambda x. So in order to, where I begin is by looking at the characteristic polynomial, which comes from this equation. Okay, a minus lambda I equals 0. So that's what I'm looking for. Okay. So in order to get that to work, first of all, I have to set up a minus lambda I. So that means I have 3051 minus lambda 0, 0 lambda. And that will give me then this matrix, which is 3 minus lambda, okay, 0, 5, and 1 minus lambda. Now what am I looking for? I'm looking at, this is my characteristic polynomial. 3 minus lambda, 0, 5, 1 minus lambda equals 0. That's the characteristic polynomial. Okay. Now in order, if I have to calculate it, of course, so that when I calculate this, it turns out to be 3 minus lambda times 1 minus lambda equals 0, which implies further, which is just, it's a quadratic, so that tells me that lambda is equal to 3 and lambda is equal to 1. So I have two eigenvalues, in fact. So I have two eigenvalues. Okay. Now you will note that what we're getting is a quadratic here. So for a 2 by 2 matrix, the characteristic polynomial is a quadratic. Okay. So for a 3 by 3, we expect a cubic. Okay, and so on. So for an n by n matrix, we expect lambda nth order polynomial. Okay, so now anyway, let's continue here. So we found the values of lambda. Our next step would be to find the eigenvectors. So we take each lambda. So here let's now consider lambda equals 1. Substitute lambda equals 1 into this main equation. Okay, but with the lambda x on the left hand side. All right, so in other words, we substitute it in here. Okay, so we set up the following system. This is what we set up. So 3 minus 1, 0, 5, 1 minus 1. And the right hand side is, of course, zeros. Now that will become, of course, 3 minus 1 is 2, 0, 5, 0, 0, 0. Now, if you reduce the matrix, even in just this one sweep, this becomes 1, 0, 0, dividing by 2, and then subtracting minus 5 times the first row plus the second row gives us 0, 0, 0. So now you see you're always guaranteed this row. Okay, a row of zeros will occur in the matrix in this system of equations. We're guaranteed that. So you need to keep this in mind. If you do not get a row of zeros after the reduction, the final system, reduced system, you have made a mistake for sure. Okay, because in theory, the value of lambda that you worked out guarantees that there are infinity of solutions, which means it guarantees that there is a row of zeros. So please keep that very important fact in mind, because it can help correct mistakes. Okay, well, it identifies a mistake in your calculations for sure. Now what we do is we will of course back substitute. So clearly x1 is 0, okay, and x2 is a completely free variable. So x2 is equal to t. So therefore our eigenvector is in fact t times 0, 1. Now here I will complete everything in one go, which is what I mean by that is the following. Now this itself is an eigenspace, okay, and it's the eigenspace of A for lambda equals 1. Okay, now each t will of course produce a vector, an eigenvector. So there's an infinity of eigenvectors, which, as we have seen in the past, one can think of as forming a subspace, and in this case it would be a subspace of R2. So it would be a subspace of R2, okay, because it belongs to R2. Now this subspace of R2, now what else do you notice here? Well, obviously this vector spans the entire eigenspace of A for lambda equals 1, and it's a lonely vector, which means it is linearly independent, which further means that this is the basis for the eigenspace. So this is a basis for the eigenspace of A for lambda equals 1. Okay, let's move further. Now, we're not done with this example yet, because we still have to find corresponding lambda equals the other eigenvalue, lambda equals 3. Now in a similar way, when we put this in, we end up with 0, 0, 0 here, and then you have 5, and you have 1 minus 3 minus 2, 0. Now you will notice that this is already reduced. The matrix can't be reduced any further, and you have a row of zeros as expected. So we will directly back substitute. Well, this implies that 5x1 minus 2x2 equals 0. Okay, so that means that if we let, for instance, x2 equal s, the parameter, then x1 is equal to 2 over 5s. That's a 5 and that's an s. Be careful there. Okay, so it's 2 over 5. So x1 is 2 over 5s. So therefore, we end up with x, the eigenvector is s times 2 over 5 and 1. So that's our eigenvector. So this, in fact, is a basis for the... Okay, so we found the second basis for the second eigenvalue. Now in this way we can also continue and solve a 3x3 matrix. So I will do that next. So we have another example here. This is a 3 by 3 matrix. That will be the characteristic polynomial you see there, the determinant of lambda minus a. Now deliberately use lambda I minus a here instead of a minus lambda I. Please keep this in mind. And lambda I, we could also, earlier, I just had this case. Okay, please keep in mind these are both equivalent. Okay, both have their advantages and disadvantages. Here you will notice that all the values in the A matrix, first of all, the nice thing is they're all lambda, lambda minus 2, lambda minus 3. However, you will notice that the values are all negative, okay, in the matrix that you see here. Be careful on that. So minus 2 is plus 2, 1 is minus 1, 1 is minus 1, and minus 1 here. But these are all lambda minus 2, lambda minus 2, lambda minus 3, and lambda. Okay, just be very careful. It could be a very high probability of making a minus mistake, so a mistake with a negative sign. So just be very careful. Anyway, from this we end up with lambda into lambda minus 2 into lambda minus 3. Okay, and then we have minus, plus 2 times lambda minus 2, in fact, equals 0. And that ends up giving us lambda minus 2 into lambda minus 2 into lambda minus 1 equals 0, which means we have a double eigenvalue, lambda equals 2, and the value lambda equals 1. Now please be wary of that all the rules for solving polynomials apply, of course, because you're solving a polynomial here. A cubic would have 3 roots, but in this it can have a double root. By the way, you can also get complex eigenvalues. However, complex eigenvalues are not included in this particular course. We will only be looking at or considering real eigenvalues. So let's move further. In this case, the next step would be to actually go to each of the values. Lambda equals 2, and the system would then be 2, 0, 2, minus 1, 0, minus 1, 0, minus 1, and of course this is our first system for the eigenvectors for lambda equals 2. So what will happen in this case is you can change the first row, of course, to just 1, 0, 1. Makes things a lot easier, and then just add it to this row, so you get the following, and add it to the third row and you get this. So now what you have is essentially the reduced matrix. We back substitute the equations, and what happens is as we back substitute, what happens is this becomes x1 plus x3 equals 0. Now let x3 equal to, say, s, which means that x1 is minus s, and of course x2 is a free variable, completely free variable. So it's a fixed free. Actually, it's a free variable, which is without an option. It can only be a free variable in this case. So x2 is equal to t anyway. So that means that we end up with x is equal to s times minus 1, 0, and 1 plus t times 0, 1, 0. So these eigenvectors, well, these are not the eigenvectors. These vectors, okay, these two vectors, let's call it the set S, okay, form a basis. Now you can check they are both clearly linearly independent, so they form a basis for the eigenspace of A with lambda equals 2. So that's a basis for the eigenspace lambda equals 2. Let's move on to the next one quickly. All right. So the next one is lambda equals 1, and that gives us this system here. Okay, as we progress to reduce this matrix, So there you have your row of zeros. And quickly, if we back substitute here, we get from the first equation we have x1 plus 2x3 equals 0. Okay, so you let r, if we let x3 equal r, then x1 is minus 2r. Okay, x1 is minus 2r. And from the second equation we see that minus x2 x3 plus x3 equals 0. x3 is r, so x2 is also actually x2 is r. Okay, it's equal to x3. x2 equals x3. So and basically we end up with this situation. We have this we have this vector. Okay, so this forms this vector here forms a basis for the eigenspace of A with lambda equals 1. So that forms a basis of the language. So that completes this example, and in fact completes our the material that we wish to cover. Now, one quick thing I will tell you is that if you have a triangular matrix or a diagonal matrix, for instance here we have, if suppose our matrix was 2 0 3 0 0 4 0 2 5 for the sake of argument, then the eigenvalues of this matrix are 2, 4, and 5. So it's the diagonal entries, in fact, that form, in fact, the eigenvalues of the matrix. Just a quick one. It goes the same for whether it's upper triangular, lower triangular, or a diagonal matrix. Thank you.